虫の呼吸、蝶の舞、たわ
蛇の呼吸、三の型。風の呼吸、死の型。水の呼吸、11の型。炎の呼吸、2の型。その呼吸、1の型。
1の型、初恋のバナナキ。
Good day, everyone. Today, our group will present how linear algebra is applied in the game 2048. In this project, we model the 2048 game board as a 4x4 matrix where each entry represents the value of a tile. By applying vector operations and matrix transformations, we convert player inputs such as left, right, up, and down into systematic mathematical operations. This demonstrates how abstract linear algebra concepts can be translated into efficient and clean game logic. Modern game development relies heavily on mathematics, and 2048 is a clear example of this. In our project, linear algebra acts as a bridge between user input and game behavior. Each keystroke triggers a mathematical transformation on the matrix, turning abstract operations into visible gameplay. Mathematical materials and definition. The game board is formally defined as a matrix of dimension 4x4. Each element Aij is a scalar from the set 0, 2, 4, 8, and so on. This mathematical structure allows us to treat gameplay as a sequence of matrix state transitions. Method 1. Matrix initialization. At the start of the game, we initialize matrix A as a zero matrix. In JavaScript, this is implemented as an array of arrays. The function setGame constructs this matrix and then calls set2. The set2 function randomly selects coordinate ij where aij equal to 0 and assign a non-zero scalar, typically 2. This introduces sparsity into the matrix, which is a key feature of the early game state. Method 2. The slide and merge algorithm. The call logic of 2048 is the slide function. From a linear algebra perspective, this function applies a transformation to a vector v. This transformation consists of three mathematical stages. Step 1. Filiation, compression. In this step, we apply a projection like operator that removes all zero entries from the vector. Example, input vector is v, which is 2, 0, 2, 0, and the output is a driven vector v, which is 2 and 2. This step reduces the vector to its non-zero components, preparing it for merging. Step 2. Combination. We then scan the compressed vector. When two adjacent entries are equal, they merge according. The second entry is replaced with 0. This operation resembles a scalar multiplication and addition, which aligns with linear algebra principles. Step 3. Dimensional restoration. Since the vector space is or power 4, the transformed vector must maintain dimension 4. We append zeros to the end, and the final vector is v final, which is 4, 0, 0, 0. This guarantees dimensional consistency across all transformations.
Method 3A. Left movement standard basis. To handle 2D movement using our 1D slide logic, we apply transformations to the matrix orientation. This allows us to reuse the same logic function for all 4 directions. For a left command, we iterate through each row index I from 0 to 3. We treat the ith row as a vector and apply the slide function directly.
Method 3b, right movement. To handle 2D movement using our one direction slide logic, we apply transformations to the matrix orientation. This allows us to reuse the same logic function for all 4 directions. First, reverse vector. The input vector is horizontally reversed to stimulate a left to right processing direction. Second, apply standard slide. The standard slide function is applied to the now reverse vector. Third, reverse vector back. The resulting vector is reversed once more to return to its original orientation, effectively completing a right movement. To move right, we use the property of reflection. We reverse the vector, mathematically reflecting it across its center. Apply the standard slide and then reverse it back.
Method 3c, up and down movement. Vertical movement operates on column vectors. We attract each column Cj and treat it as a vector. For up, we apply slide Cj directly, and for down, we reverse the column, slide, and reverse back. Results: functional accuracy. Our implementation correctly handles tile merging following powers of 2. The linear transformation logic ensures that merges occur only once per move, preserving the mathematical integrity of the game. Visual feedback. Each tile's appearance is determined by its scalar value. CSS classes dynamically update based on the matrix in choice, providing an immediate visual representation of the underlying mathematical state.
There's a lot of other factors we need to consider there, but I think that's enough in terms of the high-level explanation. So let's see what we made. So let me explain to you the process. It is a little bit complicated, then we'll begin implementing it. All right, so I'm on the drawing tablet now, and I'm going to explain at a high level what it is that we're about to do. So let's say we have the number 2. This is our tile, and we decide to make a movement to the left. Keep in mind, all the movements effectively are going to be handled the exact same. So we can just look at a case in which we're moving to the left, but the exact same thing would apply if we're moving to the right. There's just a few variables that change. So we're moving to the left and we have this tile. Now there's a few things that can happen. The first thing that can happen is there can be nothing to the left, and we can simply shift the tile. That's the easiest case, right? There's nothing to the left of us, so we just move the tile until we hit the border. Pretty straightforward. The second case is when we have a blocking tile that is in the direction of which we're moving. So again, we're moving to the left, that's where we've shifted, and now we see that when we move to the left, well, this tile exists and it doesn't allow us to move. So if that's the case, we just simply stay put, right? There's no movement that occurs for either of these tiles. Now it gets a bit more complicated, right? Where we have this tile here. So now in this case, we move until we reach a tile that is blocking us. Okay, so obviously I think that makes a bit of sense.
We've already moved it inside of the other tile, so now we'll merge it together. So those are pretty much all of the edge cases. Doing this is a little bit easier said than done because of all the things that could happen. For example, let's say we have something that looks like this, right? We have like 2, 2, 2, 2. Well, what we need to do is actually make sure that we move the tiles in the correct order such that the merges happen appropriately. So in this situation where we have 4 2s, we want to ensure that we don't accidentally merge the 2 middle tiles, because if we were to do that, we would be left with a result of 2, 4, 2, which is incorrect. What we want instead, although I guess you could define this behavior however you want, is that after we do this movement, we end up with 2 4s, right? So we delete, delete, and we have 4, 4.
Discussion. Without linear algebra, we would need 4 separate logic blocks for each movement direction. By reducing the problem to a 1D vector transformation, we reuse a single function across all directions. This reduces redundancy and improves maintainability. Conclusions and future implication. This project demonstrates that 2048 is a practical application of linear algebra. Like the board is successfully modeled a matrix, directional movement is handled using reflections and transposition. Future work could involve AI strategies that analyze matrix density or eigenvalue, like patterns, to predict optimal moves. Ultimately, this approach shows how abstract mathematics leads to cleaner and logical sound game development. Thank you for listening. We welcome any questions or discussion.